finally, 8 a.m. Good morning, guys. So let's continue. So in the previous class yesterday, we introduced Kirchhoff rules, Junction Rule, and Loop Rule. And we looked at one example. Now let's look at the second example. Okay, this time it's a problem I took it from the textbook, right? So it's a problem 63 from chapter 28, right? So let's solve one more problem and then we will start introducing something new. So again, two loop circuit, okay, reasonably complicated, right? And we need to analyze it. Again, what does it mean analyzing? Actually, what is given? First of all these parameters are given. So we have three batteries, epsilon 1, epsilon, EMF 1, EMF 2, and EMF 3. And you see the values. And resistors also given. So these are given. And so we need to analyze it. Again, what does it mean analyzing a circuit like this? Since we know everything about the batteries, so it means that we need to find currents through each of these resistors and potential differences through each of these resistors. But once you know currents, then finding potential differences are a piece of cake, right? So for example, current I1 times R1, that will be the potential difference, right? So once you know currents, finding potential differences, it's an additional minute of work, right? Okay, so now again, we introduced two methods: method of an equivalent capacity. Yeah, that will also introduced, but here method of an equivalent resistance, which can be sort of considered, and Kirchhoff rules. But method of an equivalent resistance cannot be used here because none of these resistors are connected in parallel or in series. Although it looks like graphically, again, this resistor looks like parallel to that. But again, from the point of view of physics, they are not parallel because the potential differences across this and that resistor is not going to be the same. Because we have here batteries. If you remove this battery and that battery, yeah, in that case, these two resistors would be in parallel, but not in this situation. So method of an equivalent resistance is not applicable here, right? Illegal to apply. But Kirchhoff rules, they don't have any limitations, right? So they basically truly circuit universal, right? You can apply them to any circuit. So we're going to do it. We're going to apply them here. And again, you remember before we start writing equations, junction equation, loop equation, we have to make three preliminary steps, right? And then it's much faster to write those equations. First of all, I'm not going to write three preliminary steps. Now I'm just going to show them and we'll start writing the equations. So first step, of course, you need to identify all junction points. In this case, I label this way. So this will be my junction point A, and this will be my junction point B. So that is our first step. Then second, since currents change only at the junction points, it means that in this part of the circuit, from point A to point B, in this upper part of the circuit, current must stay the same. Okay, so let's give it a name, and that current, of course, is unknown, will be our unknown. That's why you see I wrote find, but I didn't write what needs to be found, because right now, at the very beginning, I haven't introduced our unknowns. And now I'm ready to introduce what needs to be found at the end, and we will write what needs to be found, right? Okay, so a current through this part of the circuit, I will label it as I1. Direction, it's difficult to tell, actually almost next to impossible at the very beginning, right, without calculations, because here you have a battle of three batteries. Or battle of currents created by three batteries, EMF 1, EMF 2, EMF 3, right? So they're going to create the mass in this circuit, right? So of course, sort of telling exactly what's the direction of current over here, it's next to impossible. So you remember what we do in this case? We just guess a direction. And then if it's needed at the end, we can make a statement and adjust our assumptions, right? So You can pick this way, clockwise or counterclockwise. It doesn't matter. Don't sweat. Just pick a direction and follow that. I will follow what I picked in my notes. Okay, I picked this way. So this will be my current I sub 1. So I pick counterclockwise. Then, of course, again, now between A and B in this part of the circuit, again, current must be the same. Because, again, there are no any junction points between A and B. So let me label it I3. I still don't know why I picked for this current I3. Probably first, after this, I introduced current I2 through this part of the circuit. So I guess, but again, it's not a crime. And I introduced this current with this direction. So this will be my current I sub 3. And in this part of the circuit will be, of course, current I2. And which direction I picked? Okay, I picked this direction. But again, it doesn't really matter. You just need to pick a direction and use it. So these are my currents and these are my unknowns. So now I can write what I have to find. So it will be, we need to find I1, I2, and I3. These are our unknown. These are our unknowns. And again, as I said, if you want also to find the potential differences across each of these resistors, once you found currents, that's piece of cake, because you take just current I1 multiplied by R, so that will be the voltage potential difference between this resistor. Then R2 I3, R3 I2 also. Okay, so that was that is our second step. Now the last step, preliminary step, before we start writing the equations, we need to pick a travel direction. Again, any direction is good. You know what? You can ask me, so what's the difference between, for example, if you pick a clockwise direction or counterclockwise direction? How would it affect our equations? It would change the equations in this way. It's like changing a direction, travel direction. It's like multiplying the whole equation by -1. Every term will just change its sign, but it will be still the same equation, right? It's like, for example, a minus b equals 0. And if you multiply it by -1, what are you going to get? B minus a equals 0, but it's still effectively the same equation, right? So that's why I keep telling you, it doesn't matter which travel direction you pick, but you must pick a certain direction and stay with that direction or follow that direction. Okay, so for the loop number 1, I picked, okay, counterclockwise direction. Okay, let's do it. So this will be travel loop 1. That's my travel direction. And for the second, I also do the same. So that's my travel direction, and that's for loop number 2. And again, you remember what I told you about? Of course, you can say there is also an external loop, this one. But equation which that loop is going to give us will be just a sum of the equation produced by this loop and the equation produced by that one. So that will be a redundant equation, right? You can write it, but it's not needed because it doesn't give us any additional information. So every time in the circuit like this, you need to use 2 loops. Usually we use internal loops, but again, if you really want, you can apply, for example, loop number 1 and the external loop. In that case, loop number 2 is not needed. So you just need to use 2 loops all the time in this case, in the problems like this. Right. But I'm going to use loop 1 and loop 2. Okay, so now all preliminary steps are done here, and so now we are ready to start writing down the equations. And I will start with the junction rule. Okay, maybe I will write so junction rule. So you remember the total amount of current entering junction point must be equal to the total amount of current leaving that junction point. And you remember that statement which I made. If you have n junction points in the circuit, then you're going to get only n minus 1 useful equations. So every time one junction equation is going to be redundant, right? which basically it means that it doesn't give us any new information. In this case, we have two junction points, so it means that we're going to get only one useful equation. So you can pick any junction point. I will pick, for example, junction point A. Nothing wrong if you pick junction point B. So let's see. Okay, maybe I will write a rule in general. Right. And so what? In point A, okay, I will probably emphasize that it's for point A. Current I1 enters, right? And currents I2 and I3 leaves that junction point. So I can write, so I1 equals to I2 plus I sub 3. So that's our equation number 1. And again, you remember how many equations do we need? We need 3 equations because we have 3 unknowns from the mathematical point of view. Number of unknowns must be equal to the number of equations in order to solve the system of equations for our unknowns. Okay, equation number 1, and still we need to get equations, 2 equations, and of course those will come from our loops. So let's do for loop number 1, this loop. Okay, so we need to start traveling from certain point. I will start from this point. You remember my minor compulsion? I like to cross a battery first, because for me it kind of looks nice when EMF stands in front of the equation. So, and that is our travel direction. So first, it means that I need to cross this this battery. Okay, and again, every time you need to remember those 4 mnemonic rules which we introduced yesterday, right? And again, if you practice them in a couple of problems, you will remember them. Of course, if you don't use them for a few weeks, you will start forgetting, but you can easily restore them either by looking at the book or notes, or you can just easily analyze battery and resistor and restore those rules within like a few minutes. You should be able, right? But at this point, of course, for the exam, of course, they must be fresh in your head, right? So that you wouldn't waste time, right? Analyzing. So first you cross the battery, and we cross it, of course, from what? This is minus and this is plus. So we're crossing it from minus to plus. And according to the rule number 1, contribution must be positive, plus EMF. Okay, EMF 1, right? So now we cross the battery, and now we're going down through this resistor now, right, R2. And when you analyze a resistor, you need to look at both directions, direction of the current and direction of the travel. Again, when you analyze battery, you only need travel direction. Again, as I mentioned in the previous class, some even good students in the past, they got confused at this point, right? So when you analyze a battery, you need to look at the travel direction only. You only need to know which point is final, which point is initial. But when you analyze a resistor, you need to look at both directions, travel and current. Right? Don't forget that. Okay, so resistor R2, current I3 that way, travel also that way. So both directions are the same. So it means that according to the rule number 3, contribution is negative. And according to the Ohm's law, of course, it's just I3 times R2. Be careful with these subscripts, right? So negative, so it will be minus I3 R2. Okay, so that's our second term. Now let's move further. So now this resistor, this battery, sorry. Again, we travel from minus to plus. So it means, again, according to the rule number 1, contribution must be positive. Now it's a EMF 2 plus EMF 2. Okay, after this, we're going up, and now we need to cross the last element, that resistor. And what directions? A current direction that way, travel direction also that way. So both directions are the same. Contribution is negative. Rule number 3, minus Careful with subscripts, it will be minus I1 R1. And of course, the most typical mistakes, as I said, maybe like 30-40% of students, they just behead the equation by not writing the fact that it is equal to 0. No, but it must be written. It's a mistake, right? We're science majors, and we must pay attention to these details. Important. There are no any minor details in science, right? Although, yeah, some smaller effects, right, can be neglected and so on. Okay, you know what? Before I start writing the second equation, okay, the last one. Guys from electrical engineering departments, right? So probably you've seen this method somewhere in your courses, and most likely your professors used two currents method, right? So they introduced the first current in this loop and the second current in that loop. And they will write two equations, right? So that's alternative way and of course, over here in this part of the circuit, there will be sort of currents in opposite directions. So there will be superposition of currents over here, right? So it's an alternative method which can be used. It's still Kirchhoff rules, right, and so on, but it's a slightly different two current method, right? Yeah, if you're comfortable with that, okay, not a big deal, use it, right? As long as it works for you, as long as you can solve it. I remember when I was an undergrad student, our professors also taught us that two current methods. But here I look through almost all physics books which I have, and they all use three current methods like this. Because in that case, it's easier to explain physics, it's easier to justify everything than with two currents, right? Okay, so if you're okay with two currents, current method, okay, use it. Right. So now back to our equations. Now loop 2. Right. You know what? I will write underneath, because I'm afraid that I will run out of space. Yeah. So loop number 2. So what we have, again, I will start with, let's say, this point. So this will be my starting point. Again, I want to cross the battery first. So, and we're traveling this way. So first I need to cross the battery, but now from plus to minus. Now we're crossing the battery from plus to minus. It's a rule number 2. Contribution must be negative, right? You see, electric potential is going down. Contribution is negative. So it will be minus EMF 2. Right. Okay, after this we need to cross this resistor, and current direction that way. You see, red I3, but travel direction that way. So directions are opposite. So it means and we're dealing with the resistor, so it's a rule number 4. If directions are opposite, then contribution is positive, right? So it will be in this case plus I3 R2 plus I3 times R2. Again, careful with which currents you use, because here you have current I2, but in that connection in this small part of the circuit, right, so current I3. Careful with subscript of the currents. Now then, there is nothing over here. Now this resistor. Travel direction that way, current direction also that way. Directions are the same. Rule number 3, contribution is negative. Minus I2 R3 minus I2 times R sub 3, right? Okay, and after that, we need to cross the battery. And now we're crossing from minus to plus. It's a rule number 1, contribution is positive. So plus EMF 3. Plus EMF 3. And after that, we're back to the starting point. So it means that it's time to close this equation. We need to write down that it is equal to 0. So now we have 3 equations. So this is equation number, that was equation number 2. This is number 3. Okay, so now we can say physics is over. We applied all physical concepts. Now we're just a system, algebraic system, homogeneous. of three equations with three unknowns. Okay, not homogeneous, right? Forget. Just an algebraic system of three equations with three unknowns, which can be easily solved, right? Of course, I'm not going to solve it. I will just look at my notes and I will write down the answer. And then, of course, if we need, we can make an adjustments if they need it. Okay, so if you solve it, you will end up with, where is my current I1? Let me start with I1. So I1 equals to 57 over 25 amps. Okay, what does it mean? Current is positive. It means that this is the correct direction for the current I1. Well, good. Now I2. I sub 2 equals to 48 over 25 amps. Wow, again, lucky me. Current is positive. It means that this direction for current I2 is the correct one. And the last one, I3, equals to 9 over 25 amps. And again, positive. It means that even this direction of this current, I picked in the right way. Every time I keep promising myself, I need to change one of the currents in order to get negative value to say, okay, see guys, so here's the negative value. It means that my assumption about current direction was wrong, right? But still keep using these directions and getting positive values. Right?